Picture Southern California in the 1910s. Dusty roads, crude machines, and an automotive culture still learning to walk. The Ford Model T dominated the landscape, celebrated as the people's car, yet loathed by early speed enthusiasts who saw it as a slow, stubborn farm tool. It was never meant for performance, let alone climbing brutal hills. But then came a young mechanic who refused to accept that limitation. Instead of bolting on typical speed parts, he uncovered a hidden flaw deep inside the Model T's own heartbeat, then rewrote the engine's physics. And what he built defied everything Detroit believed was possible. The prodigy in the machine. Picture Southern California in the early 1900s. It is a landscape defined by dust, oil, and the deafening clatter of a single dominant machine, the Ford Model T. History remembers this car as the hero that put America on wheels. It was cheap, it was simple, and you could fix it with a hammer. But if you were a speed freak in 1915, the Model T wasn't a hero. It was a problem. Henry Ford did not build a race car. He built an agricultural utility appliance that happened to have seats. Under that hood sat a flathead four-cylinder engine designed for one thing, and that was reliability. It was an L-head design, an architecture that prioritized cheap manufacturing over actual performance. It strangled its own airflow. It had zero sporting pretensions. Trying to make a stock Model T go fast was like trying to teach a mule to sprint. It was physically possible, but the animal really did not want to do it. The engine was fundamentally an air pump that was terrible at pumping air. Yet, in this sea of agricultural slowpokes, there was a kid who looked at that breathless iron lump and saw potential. His name was Edward Arnold Winfield. And when I say he was a kid, I mean he was 11 years old. While other children were playing stickball, an 11-year-old Winfield was in the garage, stripping the bodywork off his family's Model T. He understood instinctively that weight was the enemy of speed. By removing every non-essential pound, this preteen managed to push a farm implement to 60 miles per hour. That is not just tinkering. That is a statement of intent. You might think this was just a phase, but Winfield was different. By the time he was 14, he wasn't just reading about engineering. He was in the room where history was being written. He secured a job working for Harry A. Miller. If you know your automotive history, that name should make you stand up straight. Miller was the high priest of American racing, the builder of the most exquisite jewelry-like race engines on the planet. And there was 14-year-old Ed Winfield, standing right in the carburetor department, absorbing the secrets of airflow and fuel delivery from the absolute best in the business. He wasn't a junkyard mechanic guessing at gear ratios. He was a classically trained prodigy observing the bleeding edge of race technology. This education forged a philosophy that would define his entire career. He didn't just want top speed on a flat, dry lake. He wanted grunt. He wanted torque. By age 16, he took a hand file to the cylinder head of his single-cylinder motorcycle. He opened up the intake port and reshaped the cam with hand tools. He didn't put it on a dyno. He took it to the mountains. He later claimed that after those modifications, he could climb any mountain road in the area in high gear. Hill climbing is not about how fast you can spin an engine. It is about how hard that engine can twist the tires against gravity. Winfield realized early on that to dominate the hills, you needed an engine that produced massive force at low speeds. But when he turned his attention back to the Model T, he hit a wall. He realized that the standard tricks, polishing ports or bumping compression, were just band-aids. The Model T engine was broken at a structural level. To turn that flathead into a hill climb apex predator, he couldn't just tune it. He had to fundamentally change the physics of how it breathed. Diagnosing the flathead's fatal flaw. Ed Winfield's extreme measures require us to aggressively dismantle the stock Model T engine. We need to look at it not with nostalgia, but with the cold, hard gaze of a race engineer. When you strip away the history, the Model T engine was a mechanical compromise. It was an L-head or flathead design. This architecture places the valves alongside the cylinders rather than above them. This creates a convoluted, tortuous path for the air and fuel to travel. The air has to go down, turn 90 degrees, go across the block, turn 90 degrees again, and then finally enter the cylinder. From a fluid dynamics perspective, it is a nightmare. But the breathing restriction was only the symptom. The disease was much deeper. The fundamental flaw that prevented the Model T from climbing hills wasn't just that it couldn't breathe. It was that it couldn't breathe consistently. The culprit was the crankshaft geometry and the firing order. The standard Model T firing order is 1-2-4-3. This utilizes a traditional 180-degree crankshaft. In this setup, pairs of pistons move together. Pistons 1 and 4 are up, while 2 and 3 are down. This sounds symmetrical, but when you combine it with a shared intake manifold fed by a single carburetor, you create a condition known as a fuel distribution anomaly. Think about the rhythm of that firing order. Cylinders 1 and 2 fire in immediate succession. Cylinder 1 begins its intake stroke, creating a massive vacuum pulse that rips air and fuel through the manifold. Before that column of air can stabilize, Cylinder 2 immediately opens its intake valve and tries to draw from the exact same stream. Because Cylinder 1 has already established a high-velocity flow in its direction, it effectively robs the mixture from Cylinder 2. Engineers call this phenomenon pulse stealing. It is a kinetic tug-of-war occurring hundreds of times per minute. The first cylinder in the pair gets a rich, dense charge of fuel. The second cylinder, fighting for scraps against the momentum of the air, runs dangerously lean. You end up with an engine where one cylinder is drowning in gas and the neighbor is starving. This imbalance is catastrophic for torque. A lean cylinder produces less power and runs hotter, while a rich cylinder wastes fuel and fouls plugs. You cannot tune this out with a screwdriver because the problem isn't the carburetor tuning. The problem is the timing of the vacuum pulses themselves. If that wasn't enough, the hard parts themselves were fighting against performance. Let's look at the baseline data. The stock camshaft was designed for silence and longevity, not velocity. The standard cam from 1913 onward featured a maximum lift of just 0.250 inches. That is a quarter of an inch. The valve barely cracks open. The duration was equally conservative at 218.7 degrees. These specifications meant the engine simply ran out of breath as soon as the RPM climbed. It was designed to choke itself. When early hot rodders tried to force this system to perform, by bolting on high compression heads or advanced ignition systems without addressing the underlying flow issues, the results were often explosive in the wrong way. The uneven power pulses from the starving cylinders caused terrible vibration. The stock crankshafts, which were never designed for high-load harmonics, would often crack under the stress of mountain driving. The planetary transmission, screaming to handle the torque spikes, would shear drive plates. Ed Winfield looked at this mess of physics and realized something profound. You could not fix this engine with bolt-on parts. You couldn't just put a bigger carburetor on it, because a bigger carburetor would just feed the imbalance more fuel. The engine was structurally incapable of equalizing the charge. The bottleneck wasn't the intake, it was the rotation. To build a hill climb monster, he didn't need a tune-up. Winfield's radical kinetic redesign. The solution Ed Winfield devised was not a modification, it was a mutation. And he recognized that the only way to fix the breathing problems of the Model T was to tear out its spine and replace it with something completely different. This innovation is what separates a mechanic from an engineer. He introduced the 2-up, 2-down engine architecture. To understand the magnitude of this change, look at the standard Model T crankshaft. It is a 180-degree unit. That means at any given moment, 2 pistons are at the very top of their stroke, and 2 are at the very bottom. It is a symmetrical, rhythmic dance that Henry Ford designed for low-speed manufacturing. Winfield looked at that steel forging and saw a prison. His approach centered on designing and utilizing a custom crankshaft that fundamentally altered the relative phasing of the pistons. This new geometry changed the relationship between the cylinders. Instead of the chaotic pulse-stealing rhythm where one cylinder robbed the next, the 2-up, 2-down configuration synchronized the pistons to create a highly uniform vacuum signal throughout the shared intake manifold. By precisely controlling the temporal spacing between consecutive intake strokes, Winfield ensured that the violent vacuum drawn by one cylinder did not disrupt the mixture being pulled by the next. The result was the elimination of the negative pressure wave interactions. Suddenly, the fuel charge was homogenized. Every cylinder received an equally potent volume of air and fuel. In terms of physics, this is the maximization of volumetric efficiency, or VE. VE is simply the ratio of how much air you actually get into the cylinder compared to how much it could theoretically hold. The stock engine had terrible VE because of the uneven pulses. The Winfield engine, with its structural redesign, achieved a huge gain in performance because it finally allowed the atmosphere to fill the cylinders without fighting against internal turbulence. This massive increase in efficiency translated directly into smooth, reliable, low-speed torque, the exact kind of immediate, sustained power required to launch a car up a 22% grade. But having a theoretical design is one thing. Building it in the 1920s is another. The shift in kinetic dynamics necessitated a corresponding, highly specialized valve train. You cannot run a radical crankshaft with a stock camshaft. The valve timing would be completely wrong. Winfield had to fabricate custom camshaft profiles to optimize duration, lift, and overlap for this new piston movement. This is where the story shifts from clever engineering to absolute mastery. The unique specifications of the 2-up, 2-down cam design were so radical that conventional grinding machinery could not produce them. The standard Landis grinders used for Model A or V8 cams were useless for the geometry Winfield needed. A normal mechanic would have compromised. Winfield did not. He was compelled to design and build his own dedicated cam grinder. He literally built the machine tool to build the part. This level of vertical integration, designing the theory, building the tool, and manufacturing the component, confirmed his transition into a pioneering performance manufacturer. The system did not end there. Winfield knew that this new monster engine would generate dynamic forces far beyond what the stock components could survive. To manage the increased power and rotational stress, he engineered lighter yet stronger internal components. He utilized aluminite rods to reinforce the custom crank assembly. These reduced the reciprocating mass, allowing the engine to rev freely while maintaining the structural integrity needed to survive the brutal torque of a hill climb. Unleashing the airflow catalyst. The 2-up, 2-down crankshaft was a masterpiece of structural engineering, but it created a new problem. This is a classic case of the law of unintended consequences in engine building. By synchronizing the vacuum pulses and maximizing volumetric efficiency, Winfield had essentially turned the engine into a vacuum pump with an insatiable appetite for air. The engine was finally ready to breathe deeply, but the standard carburetor was choking it. This is where Ed Winfield introduced his second revolutionary innovation, the barrel throttle carburetor. If you know anything about vintage racing, you know the name Winfield is synonymous with carburation. His carburetors were not just popular, they were mandatory. From 1933 through 1946, practically every winning car at the Indianapolis 500 ran a Winfield carburetor. The only exceptions were the Italian Maseratis in 39 and 40. That level of dominance doesn't happen by accident. It happens because of superior flow dynamics. His early retail models, the Model H and Model V, and later the Model M, were the weapons of choice for anyone who wanted to win. The secret lay in the throttle mechanism itself. Almost every other carburetor on the planet, then and now, uses a butterfly valve. A butterfly valve is a flat metal disc mounted on a shaft in the center of the carburetor throat. When you step on the gas, the disc pivots to let air through. It is simple and cheap to make, but from an airflow perspective, it is flawed. Even when a butterfly valve is fully open, what we call wide open throttle, or WOT, the metal plate and the shaft are still sitting right in the middle of the airstream. They create turbulence. They block flow. They are an obstruction in the very throat of the engine. Winfield looked at that obstruction and decided to eliminate it. His solution was the barrel throttle. Instead of a flat plate, he used a rotating cylinder, a barrel, with a bore precisely matching the carburetor throat. When you closed the throttle, the solid side of the barrel blocked the air. But when you rotated it to the fully open position, the bore of the barrel aligned perfectly with the throat. The obstruction disappeared. It created a completely smooth, unrestricted tube for the air to rush through. It effectively became a straight pipe. This design difference sounds subtle, but the numbers tell a violent story. Technical analysis of flow dynamics demonstrates that while a butterfly valve might be slightly more efficient at very low throttle openings, say up to 30 degrees, it becomes a liability when you really need power. At throttle openings beyond 70 degrees, the barrel throttle pulls ahead significantly. Studies indicate that at wide open throttle, the Winfield barrel design can achieve an increase in mass flow rate of up to 34% compared to a standard butterfly valve. 34%. In the world of engine tuning, where people fight for gains of 2 or 3%, a 34% increase in airflow capacity is not an improvement. It is a completely different category of performance. It is the difference between breathing through a straw and breathing through a snorkel. Now, connect this back to the hill climb. This is where the application dictates the design. When you are attacking a 22% grade like Signal Hill, you are not feathering the gas. You are mashing the pedal to the floor and holding it there. You are living at wide open throttle. In that specific condition, the stock carburetor would be a restrictor plate, starving the engine of the air it needs to make torque. The barrel throttle, however, acts like an open floodgate. It ensures that the massive air demand created by the high-efficiency 2-up, 2-down engine is met without resistance. The engine demands the air, and the carburetor supplies it without turbulence or pumping losses. It was a synergistic pairing. The crank created the hunger, the carb provided the feast. This integration of a high VE engine structure with a low-restriction delivery system maximized the power density achievable from the small Model T displacement. The hill climb reality check. All of this engineering, the custom crank, the radical firing order, and the barrel throttle would be meaningless if it did not translate into one thing: dominance. In the 1920s, you did not prove your car on a dyno sheet because dynos were not exactly common. You proved it on the hill. The ultimate proving ground for Southern California hot rodders was a place called Shell Hill in Signal Hill near Long Beach. Shell Hill was a monster. It was a 1/10 of a mile of dirt and asphalt that shot straight up at a 22% grade. To give you some context, a modern interstate highway is legally capped at a 6% grade. Shell Hill was nearly 4 times steeper than the steepest highway you have ever driven. Conquering a grade like that is not about top speed. It is about violent, sustained torque. It is a test of whether your engine can fight gravity and win. A stock Model T, with its wheezing flathead and 20 horsepower, would struggle up that slope like a dying animal. It typically took a stock T between 25 and 30 seconds to crawl to the top, often boiling over in the process. The drivers were practically pushing the pedals through the floorboards, praying for momentum that never came. But when Ed Winfield showed up with his 2-up, 2-down equipped speedster, the clock told a different story. Winfield's car, often referred to by the press as the fastest Ford in the world, did not just climb the hill, it attacked it. While stock cars were taking half a minute, Winfield's machine was blasting to the summit in under 9 seconds. Think about that delta, 9 seconds versus 30 seconds. He was not 10% faster. He was over 300% faster. In the world of motorsports, that is not a victory. It is an annihilation. It is the difference between a biplane and a jet fighter. This dominance was the ultimate validation of his theory. That 9-second run proved that the homogenized fuel charge was working. It proved that every cylinder was firing with equal force, generating a seamless wall of torque that pushed the car upward without hesitation. The barrel throttle was wide open, feeding the beast, and the custom cam was managing the valves with surgical precision. The engine wasn't fighting itself anymore. But there is another layer to this victory that is often overlooked, and that is durability. Winfield was not the only guy trying to go fast. Other mechanics were throwing nitrous, high compression, and weird fuels at their Model Ts. But their cars often did not make it to the top. The stock crankshafts would crack under the strain. The planetary transmissions would explode because of the violent vibrations caused by uneven firing. You see, when you force a stock, unbalanced engine to make power it wasn't designed for, the metal gives up. Winfield's car did not break. He had engineered the entire system, not just the power. Remember those aluminite rods and the custom heavy-duty crank? They were not just for show. They were there to handle the immense structural loads he was creating. He built a monster engine, but he gave it the skeleton of a giant. He understood that to finish first, you must first finish. His competitors were driving grenades with the pins pulled. Winfield was driving a weapon system. This durability combined with that 9-second speed made Winfield a legend. He proved that you could take the most basic utilitarian vehicle in America and, through rigorous scientific re-engineering, turn it into an apex predator, defining the American hot rod. Ed Winfield's celebrated weird trick was not a simple bolt-on component or a minor adjustment. It was a radical, structural re-engineering of the internal combustion engine's most fundamental kinetic system. The innovation was the design and implementation of the 2-up, 2-down custom crankshaft and its corresponding camshaft profile. This system was specifically engineered to overcome the Model T's inherent flaw, which was the unequal distribution of the fuel charge caused by the standard 180-degree crank and firing order. By altering piston synchronization, Winfield equalized the vacuum pulses in the intake manifold, maximizing volumetric efficiency and extracting a huge gain in performance. This was primarily manifested as sustained, consistent torque, which was the specific requirement for his success as a hill climb monster. The Model T hill climb monster was the result of a holistic engineering system that married structural perfection with optimized fluid dynamics. The corrected engine dynamics of the 2-up 2-down crank created the demand for consistent airflow, which was then perfectly supplied by Winfield's innovative, low-restriction, barrel throttle carburetors. But Winfield's impact goes far beyond a fast Model T. His true legacy is the democratization of speed. Remember, he started his career in the exclusive, expensive world of Harry Miller, where racing technology was reserved for the wealthy. Winfield took those rigorous, high-precision standards and brought them down to the street level by manufacturing and selling specialized components like his Model M and S carburetors. He allowed the average mechanic in Southern California to incorporate professional-grade technology into accessible platforms. He moved the performance culture beyond simple experimentation and bolt-ons toward a rigorous scientific approach centered on understanding and eliminating mechanical bottlenecks. This ability to move performance from the exclusive realm of wealthy racers into the hands of mechanically inclined young men defined the true beginning of the American performance aftermarket industry. When you buy a part for your car today, you are participating in an economy that Ed Winfield helped invent. He is the spiritual grandfather of the Speed Equipment Manufacturers Association, or SEMA. Ed Winfield proved that you don't have to accept the limitations of the machine you are given. If you understand the physics and you have the courage to cut the metal, you can turn a farm tractor into a hill climb legend.